This video is confidence intervals one population mean for a normal distribution. Suppose your company makes iPhone cases and you want to ensure their quality, specifically the dimensions. How can you check the average width, let's say, of all the cases you make so that you know they'll fit properly? Well, you could theoretically measure every single case, but in a big production facility, this isn't feasible because the time and effort that it will add will cut into your profits. Instead, you can take a small sample, measure the average width in your sample, and use that to estimate the average width of your population. We can do better though. The sample mean is simply a point estimate of the population mean. But in this chapter, we'll find how to come up with an interval that estimates the mean. So first, some terminology. You're going to hear the words point estimates. You're going to be asked, what is the point estimate? It is a single number that estimates a parameter. So many times what we're going to be estimating is the mean or the proportion. So the single number that will estimate the parameter, a parameter is a population mean or population proportion, a number that describes a population. So if we're trying to estimate the population mean, we're going to use the point estimate, which would be the sample mean, which is x bar. Or we will use something called p hat, which represents the sample proportion. More on p hat later. We're going to use the point estimate to calculate a confidence interval. That's what this whole chapter is about. And a confidence interval is a range of numbers that gives a lower and an upper bounds on what a parameter is likely to be. So you could say, well, for our confidence interval, the mean can be anywhere between 19.8 and 20.2. So you can't narrow down the mean to a specific number, but you can narrow it down to a range of numbers. So instead of saying, I think the average width of our iPhone case is 67 millimeters, you could say, I'm 95% confident that the average width of our iPhone cases is between 66.8 and 67.2 millimeters. So we've narrowed it down to a range rather than just a number. And that's actually more feasible than actually being able to estimate the actual mean of the entire population, because the population is just too huge to be able to get the actual number. But we can narrow it down to a range. So here's some other things to consider. There's a confidence level. We have what's called a confidence level. In this case, it was 95%. So when we go back here, you see that confidence level right here. When we state a confidence interval, we usually state a confidence level with it if we don't know that there is a confidence level, whether it's published or not. So our confidence level in that case was 95. The person making the confidence interval typically decides what the confidence level they want to use is usually 90% or above. So it's basically, how confident are you? What it means is to be 95% confident. For instance, 95% confident, it would mean that if you repeated this process over and over and over again, 95% of the time, whatever you find will be accurate. It will accurately estimate the true mean or the true proportion, whatever we're doing. If our confidence level is 90%, it means if we repeated this over and over again, 90% of the time, our confidence interval would contain the true parameter. Confidence intervals are symmetric about the point estimate. So think of, we're used to seeing normal curves, so think of symmetric bell shape. So the point estimate, the mean, that's your sample mean, or when we're doing proportion, be your sample proportion. So your confidence interval let's say it's those 2 points there, whatever the distance is between this point estimate and this lower boundary is the same distance between your x bar and the upper boundary, so it is symmetric. Then we have something called the margin of error, and it's the distance from the point estimate to the edges of the confidence interval. So this distance here that I was just talking about, that is your margin of error, and the margin of error is also over here. So in this case, so for the confidence interval that was stated earlier about the iPhone cases, the margin of error is 0.2 millimeters. So the confidence interval could be written as 67 plus or minus 0.2. So 67 would be in the middle, plus 0.2 would give you 67.2, minus 0.2 would give you 66.8, which is what the confidence interval they gave on the previous slide was. So this is another way to write your confidence intervals, instead of writing it with the lower boundary and the upper boundary, writing it with the point estimate plus or minus the margin of error. So let's talk about constructing a confidence interval. So first we have some assumptions that we need to make. One, when we're doing the method I'm going to show you in this video, we should know the population standard deviation, lowercase sigma. You have to know that. And if we do know that, then one or two things have to be true. Either the population is normally distributed, or the sample size is larger than 30. So think about central limit theorem. When it's greater than 30, then the distribution of the sample means would be normal. So it's either already normal, or the sample size is large and it's greater than 30. And again, I've already told you this is so important. You have to know the population standard deviation. Now, they may say the population standard deviation is 0.2, or they might say sigma and use the actual notation is 0.2. Or they may not use either one. They may not use the word population. They might not use the notation sigma. They might say something along the lines, it is known from previous studies that the standard deviation is 0.2. So when you're referring to previous studies, that's referring to a population parameter that was found. So make sure you know the population standard deviation, because remember, there's another standard deviation that we can find, and that's sample standard deviation. So make sure they're not giving you sample standard deviation, because that changes our process a little bit. So make sure that the population is normally distributed or has a sample size bigger than 30, and that the population standard deviation is known. So then we recall the central limit theorem. Remember, when the sample size is bigger than 30 or it's normally distributed, you can assume that the sample means are normally distributed, and that the mean of the sampling distribution is the same as the population mean, and the standard deviation is the standard error, which is the standard deviation over the square root of n. So that is a review from the last chapter that we did. And so that's going to come into play here. So example 1, battery life. So some of this is a little bit of a review, but it's going to help with the big overall picture. A battery manufacturer claims that the lifetime of a certain type of battery has a population mean equal to 40 hours and a standard deviation of sigma equals 5 hours. That means, because they use sigma, that means that standard deviation is a population standard deviation. Let X represent the mean lifetime of batteries in a simple random sample of size 100. If the claim is true, what is the probability that X is less than or equal to 39.8? So I'm going to kind of draw a very flat looking normal distribution. Now, this is not normally distributed. Well, it could be, it just doesn't say that it is. But since X represents the mean lifetime of the batteries in the simple random sample, it basically represents, it represents X bar, is what it really represents. I'm going to put that up here too. So X bar. So if the claim is true, what is the probability that X bar is less than 39.8? So remember, the center is the mean, which is 40. 39.8. It's not letting me write the 9. Sorry. Okay, 39.8. That's a little smush, but it's right there. So what's the probability that it's less? So let me change the ink a little. So this would be normal CDF, and we're going from negative infinity to 39.8. That's a 3 there. Followed by the mean, which is 40. Followed by the standard error, because it's for a sample. So 5 over the square root of 100. And we get 0.3446. So based on the answer to part A, if the claim is true, remember the claim is that the mean is 40 hours, is a sample mean lifetime of 39.8 hours unusually short? Well, the probability that it's less than 39.8 is 0.3446, which is not less than 5%, so it's not unusual. So if the sample mean lifetime of 100 batteries were 39.8 hours, would you find the manufacturer's claim to be plausible? So the claim is that it's 40, and I found the mean lifetime is 39.8. I think because if it was 40 and the probability that it could be 39.8 or less is basically 34.46%, it's a pretty decent chance there. So it is plausible that when it's 40, you could get an average of 39.8 in your sample. So yes, it is definitely plausible. So if the claim were true, what is the probability that X is less than or equal to 38.5? So I've drawn out the diagram here. We want less than 38.5, so we did normal CDF, negative infinity to 38.5, 40, 5 over square root of 100, and I got 0.0013. So based on that answer, if the claim is true that the mean is really 40, is a sample mean lifetime of 38.5 hours unusually short? Well, it has a very low chance of happening, less than 1% chance of getting that if the mean is really 40. So yes, it is unusual. This is definitely less than 5%. It's way less than 5%. So if the sample mean lifetime of 100 batteries were 38.5, would you find the manufacturer's claim to be plausible? Well, in this case, the chance of that happening is only, like we said, less than 1% chance of that happening. If the true mean is 40, it is very unlikely for you to get a sample mean of 38.5. So the manufacturer's claim is not plausible. Okay, we're going to stop here at the 14-ish minute mark and pick up with part 2 on the next slide.